The next speaker is Maksym Ovchynnikov from Leiden, and he will also continue the subject of HNLs and bounds on them, and he will also remind you about the SHiP experiment and its physics reach for new physics. Maksym, are you here?
Hi. First of all, thank you for providing an opportunity to give a talk at this workshop. Let me share the screen. Let us first start about with some introductory about intensity and energy frontier. So we all know that new physics particles may couple to the standard model either via high dimensional operators, which are typically suppressed and require large energy scale in order to reach them, or portals and renormalizable operators, which may be classified in accordance to a particle which we are interested in. So scalar portal, which introduces a dark scalar, vector portal, which introduces in particular dark photons, neutrino portal, which introduces heavy neutral leptons or HNLs. While searching for Higgs bosons, people naturally pushed the energy frontier, and the intensity frontier remained unexplored. But now it becomes more and more important to push also the intensity frontier, as we need to search for some particles which may be a solution for beyond the standard model problems. So LHC itself in high luminosity phase, in principle, is also able to explore the intensity frontier. However, and the same is true for some future colliders, in particular FCC. However, there is a problem. Typically, it is complicated to probe a small mass range, in particular masses lower than B meson mass at LHC. Just because, first of all, particles that have such low masses typically have long lifetimes, and therefore a large decay volume is required to look for something for their decays in particular. And second, it is complicated to deal with background at such low masses. So in particular, displaced vertices search schemes at LHC typically operate with the invariant mass cut mass higher than this B meson mass, and that is why it is a problem. So having this mass range, we're interested in how small couplings are which we are looking for at the intensity frontier. So we may consider, for instance, HNLs. So obviously the upper bound on the couplings, which we need to look for, are imposed by some of old experiments such as Charm, Delphi, and so on. And what about the lower bound? The lower bound corresponds to long lifetimes, and naturally it comes from cosmology and astrophysics. Another bound for HNLs is it is specific to HNLs, is a requirement for them to provide masses to active neutrinos, which pushes the seesaw bound. So let us discuss a cosmological bound in more detail. So the earliest messenger from the universe, which is more or less robust, is BBM. So we observe primordial abundances, such as helium, deuterium, and so on. And particles, if they are long-lived enough, so if their lifetimes is higher than 10 to the minus seconds, they may affect these abundances via different mechanisms. In particular, if an HNL has mass higher than the charged pion production threshold, it may produce an instant population of pions while decaying. And if these pions survive, if these pions are present around neutrino decoupling and neutron decoupling, they may lead to an overabundance of neutrons, and in this way to the overabundance of helium. And this effect is very strong. It is stronger than any other effect of HNLs on BBN previously considered in literature. And in particular, it allows imposing the bound on HNL lifetime around 0.02 seconds. This is a factor of 5 smaller than the bound which is typically used in when considering constraints on HNLs. So combining bounds from BBN, a requirement that HNLs provide masses to active neutrinos and and explain their oscillations. So neutrino mixing mass angles and phases in particular, and also old experiments allow us to impose a lower bound also on the HNL mass in a neutrino minimal standard model, which deals with HNLs that explain neutrino oscillations and also baryon asymmetry of the universe. So this is a recent work in which this has been obtained. So this mass is around 100 MeV, and it will be pushed to around 300 to 400 MeV in the nearest future when some of the experiments such as Na62 will increase their intensity. So similarly, same picture is true for other portals like dark photons or dark scalars. So we typically have a lower bound caused by astrophysical and cosmological constraints, and we have the upper bound caused by old experiments. So given that LHC is not able to probe this domain in a good manner, we need some experiment which may cover this important parameter space. And turns out that a very, very good experiment which may do this is a SHiP experiment. So it is an experiment planned to be located at SPS. It is a beam dump experiment. So high intensity beam of protons with the energy of equal to 400 GeV collides with a thick Wolfram target. Then produced particles, including standard model particles and new physics particles, they pass a system of hadron absorber, active muon shield, which efficiently stops this potential background. Then they reach a neutrino detector, which is expected to study neutrino scatterings and also scatterings of some new physics particles, including dark matter candidates. And afterwards, they reach this hidden sector decay volume, which is around 50 meters long, and its main goal is, of course, to study decays of weakly interacting particles. So a system of active muon shield, hadron absorber, and also trigger veto, which surrounds this hidden sector decay volume, it decreases background to a very, very low level. And in particular, for many models of new physics, this background is practically absent. And further detectors, calorimeter system, spectrometer system, are allowed to reconstruct very accurately kinematics of particles, including vertex reconstruction, including mass reconstruction if decay products are all visible, and so on. So detector is placed on axis. It covers very forward direction. And this coverage is designed in order to, on the one hand, maximize the acceptance for new physics particles that reach this decay volume, and on the other hand, to reduce the background from long-lived muons that, despite this muon shield, may still reach this decay volume. But because of this design, this muon flux is minimal. So yet not yet not accepted, SHiP is planned to be installed at the beam dump facility, which has already been funded for design and development studies. So this beam dump facility delivers really using slow extraction, delivers very intensive proton beam, and it is planned to be located at, as a branch of existing SPS tunnels. So here it is, and this is SHiP in this beam dump facility. So let us discuss what SHiP may tell about portals. So first of all, there are two kinds of sensitivity. The one which is based on the number of events, such that we require, knowing that some particle exists, we require, say, 10 events in order to find it. Or based on the ability to reconstruct some parameters of models, so mass, some specific couplings, and so on. So first of all, considering the number of event sensitivity for SHiP, we find that it covers a huge parameter space, and the lower bound of the sensitivity, which covers the minimal probed mass, mixing angles, is very, very close to this seesaw bound, and bound caused by BBN. The same is true for other portals, at least. However, despite the fact that for them the difference between the lower bound of SHiP and the upper bound from astrophysical and cosmological bounds is different, is somewhat higher. That is because parametrically lifetimes of these particles, HNLs, scalars, dark photons, they behave differently with coupling. At the given mixing angle, the decay length for dark scalars and dark photons is much shorter than for HNLs. That is why there is a huge difference as compared to SHiP here, to HNLs here. Let us now be more specific and discuss the sensitivity to reconstruct parameters, and let us consider a case of HNLs. So first of all, HNLs, unlike dark scalars and dark photons, have a decay channel, semi-leptonic decay channel, like decay into a lepton and the pine. So we may clearly distinguish this HNL by this channel. So a few decays is required. Then, apart from that, there are HNL mass, mixing pattern, so mixing two different lepton generations, number of HNLs. And also, we know that in order to explain neutrino stellations and baryogenesis simultaneously, we need to have two HNLs which are closely degenerate in mass. And this mass degeneracy makes an important conclusion on the phenomenology of HNLs. So two HNLs oscillate with a period inversely proportional to this mass splitting, and if the corresponding length scale is much higher than the scale of the experiment, that SHiP in particular, so then these two HNLs behave as a Dirac particle. In the opposite limit, if this scale is shorter than the experiment scale, then they behave as a Majorana particle. And if this period is comparable with the scale of the experiment, we may resolve these oscillations, and in particular be able to reconstruct this mass splitting. So it turns out that SHiP in principle is able to probe all of these parameters. So mass may be extracted from decays in which all decay products are visible. These decays are relatively often. Then Dirac or Majorana nature of HNLs may be distinguished by comparing the spectrum of decay products. It turns out that they are somewhat different because of the helicity conservation in the by observing a significant amount of events, it is possible to distinguish between these natures. Then we may try to extract these mixing patterns by observing a lot of decay events, and use the fact that the branching ratios for these decay events are independent on the overall mixing angle value, and around 1000 of events is expected to check whether the given HNL corresponds to the inverse or normal hierarchy of neutrino masses. So, however, despite significant reach in the probed couplings at the intensity frontier, SHiP is not currently approved, and after its proposal, a very huge amount of the intensity frontier experiments have been proposed. They include SPS-based, such as Na62 in the beam dump mode, and shadows proposed by Gaia, LHC-based experiments such as Phaser, Methuselah, and Codex B, Anubis, and so on, Dune, which is at Fermilab, and other experiments. So we need, it would be good to compare sensitivities of these experiments in some clear and uniform way. Because typically people operate by Monte Carlo simulations, and this does not allow us to understand qualitatively why one experiment has better sensitivity than the other experiment. So in order to make this comparison properly, we introduce a very simple analytical description of the decay for the amount of decay events. So obviously, in order to detect a particle which is feebly interacting, we need it to be first produced and then decay. And being produced, this particle must reach the decay volume, and its decay products must reach the detector and then be successfully reconstructed. And of course, this particle has to decay inside the decay volume, and this means that at the upper bound of the sensitivity, when the decay length is smaller than the distance to the decay volume, the number of events is exponentially suppressed, while at the lower bound, where we are in the opposite regime, the number of events scales linearly with the coupling squared. So, having these simple formulas, we may estimate characteristic features of the sensitivity. So, for the upper bound, the main factor which determines the behavior of it is this exponent. And roughly, within a factor of u, the upper bound is proportional to this combination. So, the average momentum of a particle that decays divided by the distance to the decay volume. At the lower bound, the scaling is instead a square root form, which is because at the lower bound, the number of events scales as coupling to the force. And we have now parameters which we need to estimate in order to compare all of these intensity frontier experiments. So the intensity roughly, the total acceptance, and this fiducial length, minimal length to the decay volume, and the average momentum. So the intersection of the upper and the lower bound determines the maximal mass which is to be probed. That is why the upper bound is of particular importance. So we will compare potentials of all of these experiments. So Na62 in the regime of increased intensity of the beam, shadows, Phaser 2, Methuselah. Yes?
I think you can do this comparison very quickly because we are running out of time.
Okay. So typically these portal particles are produced either in the case of mesons, if we have GeV scale, or in proton bremsstrahlung. So we may compare main numbers for these experiments. So we see that SHiP has much higher intensity than LHC based experiments, and A62 and shadows, they have somewhat lower. SHiP, Phaser 2 and Na64, they are on axis, while shadows and Methuselah are off axis. And this determines main features of this of the lower and the upper bound. So despite smaller angular coverage, SHiP and A62 and Phaser 2, they have a significant amount of protons, of mesons and particles from Bremsstrahlung to deliver sufficient sensitivity. On the other hand, Methuselah and shadows, they are off axis, and it is complicated to probe particles produced via Bremsstrahlung because they have typically small transverse momenta. So the decay acceptance is significant, needs to be estimated only for for experiments with long decay volumes or small energies, because in this case, characteristic angle between decaying particles becomes comparable with the angle of detector seen from the beginning of the decay volume. So for Methuselah and Phaser 2, these decay acceptances are of order of 1, and for SHiP and shadows, they are of order of 0.1, and for an A62, it is even smaller because the detector system is very long. So combining all these numbers, we arrive at the conclusion that SHiP is very competitive for production from D mesons and Bremsstrahlung, and also for B mesons. It is somewhat worse than Methuselah because Methuselah has significantly lower average momentum. Here is minus first, should be. This is for the lower bound. For the upper bound, we have the situation that SHiP is better for Bremsstrahlung and shadows is better for the production from B and D mesons because it is located much closer to the target. But as a conclusion, we see that SHiP is, a kind of a golden rule experiment which may probe all of these portals. So these estimates, very simple estimates, they are in good agreement with more complicated simulations, and we see that as expected, this upper bound of SHiP is much better than the upper bound of competitors, including Methuselah, except for Phaser 2, which is comparable. The lower bound of SHiP is much better than for Phaser 2, for instance. It is somewhat worse than for Methuselah, but the difference is not very significant. And the maximal mass probed at SHiP is higher than at Methuselah. So we conclude that in range of masses below the B meson mass, SHiP is a very, very good experiment. And despite a huge amount of intensity frontier experiments which have been proposed in the meantime, still this option, this goldenness of SHiP is preserved. So actually this is conclusion. Thank you for attention.
Thank you very much. Any questions to Maksym?